Hi, today we're going to be talking about Transport 2, Exam 2. And so the situation given is a convective mass transfer. And this is a circular pipe with a liquid moving down the inside surface of the pipe, and gas is blown upwards through this pipe. So at that liquid interface, we're going to be seeing that a mass transfer between the liquid and gas phase. And what we're interested in this problem is the mass transfer coefficient. So what we want to do is we want to collect experimental data, but before we do that, we want to perform a dimensional analysis so we can reduce the dimensionality of this problem. And so what we're going to be doing now is we want to establish that the Sherwood number, the Reynolds number, and the Schmidt number are going to be good dimensionless groups for this problem. So let's get started. All right, so what we want to do first is we want to identify the units and the variables that will apply to this problem. So let's first start with the mass transfer coefficient, since that's what we are interested in. And then since it's a moving liquid and a gas, we are going to be looking at velocity, and then density for those components, and then viscosity, since it is a liquid, and the diffusion coefficient for that mass transfer, and a characteristic length, in this case, which is diameter of that pipe. So the units that are all involved with these variables are kilograms, meters, and seconds. And these will be important throughout the problem. So what we want to do now is we want to create this design matrix by filling it out. So looking at the mass transfer coefficient, we are going to see that it's in units of meters per second. So there's no kilograms. Meters are going to be in the numerator, and seconds is going to be in the denominator. And that's how we're going to continue filling out this design matrix. So velocity, that's also in meters per second. So same thing. Density is in kilograms per meters cubed. So 1. Oops. So -3, since it's cubed in the denominator, and there are no seconds for this. Viscosity is going to be kilograms per meters per second. So 1 here, and these will both be in the denominator. And then for the diffusion coefficient, that's going to be in meters squared per second. So there's not going to be any kilograms. There will be 2 for the meter squared, and then per second, just a -1. And then diameter, which is just the length, we'll just have meters. So now from here, we want to look at the rank of this design matrix, because the number of variables, which there are going to be 6, n is going to equal 6. The number of variables minus the rank is going to give us the number of dimensionless groups that are going to be involved in this problem. So what we're going to do is go to Google Collaboratory and find out the rank using code. All right, so now what we want to do is we want to find the rank for the design matrix that we just made. So we're going to use NumPy. And we're going to use numpy in the linear algebra function. It's a matrix, and we want to find the rank. Okay, so now let's input those values going across the rows. So looking at the design matrix, I'm going to put the kilogram values correlating to the variables first. So 0 for that mass transfer coefficient, 0 for that velocity. There is a kilogram or mass in the numerator of the units for density. And then so on for the rest of the variables. Now we're going to do the same thing for the meters. So let's see. Remember, those negatives mean that those units are in the denominator of the units for the entire variable. So like this, -3 over here is for meters cubed in the denominator for density. So kilograms per meters cubed is what it is. Now on to the last one. We can try this. So the last one is seconds. Let's just do that real quick. Let's make sure we have all the commas we need. All right, that looks good. Shift Enter. Oops. Oops, forgot a comma there. I did forget one. All right, and then we get our rank of 3. And now we can move on with the rest of our problem. Okay, so now that we know the rank of this design matrix, we want to do the number of groups of the variables minus the rank, which is what we found to be 3. And we get that we are going to have 3 dimensionless groups. So now what we want to do is use the Buckingham Pi method to evaluate these 3 dimensionless groups to find these 3 dimensionless groups that are going to be appropriate for this problem, because it's going to make solving this problem overall easier, and we'll in the end be able to plot these dimensionless groups, which we wouldn't be able to, or would be a lot more difficult otherwise with dealing with all 6 of these variables. So this rank 3 represents these 3 dimensionless groups, and so we're going to have 3 expressions. So we're going to have pi 1, pi 2, and pi 3. So the only rule for this is that we are going to have a set of core variables, which in our case will be 3, and those core variables must all include these key units. So in combination together, they need to include kilograms, meters, and seconds. So there's no real wrong way to do this. A way to reduce or to figure out maybe what you want to isolate for your non-core groups, which there will be one at the end of each of these dimensionless groups, would be to say maybe I'm interested in finding the mass transfer coefficient, so I would maybe want to put that as a non-core group, but that's just preference. So in my case, I'm going to just decide to do the first pi group, and the set of core groups I'm going to use for each of these dimensionless pi groups are going to be diffusion coefficient, the density, the diameter, which is just the characteristic length. And then the first non-core group I'm going to be interested in is going to be the mass transfer coefficient. And for each of these core groups, we're going to put a coefficient. So A, B, okay, that looks bad. Let's redo that. I'm putting A, B, and a C. So then we do the same thing for pi 2. But this time we're going to be interested in having the non-core group be velocity. And then our third pi group is going to be this. And we're going to be interested in the viscosity. Okay, so now what we want to do is we want to find the coefficients for each of these dimensionless groups. So what we're going to do is we are going to look at the units because these are going to be dimensionless groups. So we want to have the exponents where it will be dimensionless. So let's look at pi 1. So the diffusion coefficient is in meters squared per second. Density is in kilograms per meters cubed. And that diameter is just in meters. And that mass transfer coefficient is in meters per second. So now looking at this, let's look at this group here. We notice that this is the only variable that has kilograms in it. So that means that this B is going to need to be to the 0th power. So that's taken care of. Now let's look at the variable of meters. So looking at this first group, we see that there's meters squared in the numerator. So that's going to be 2a. And then this is going to be 0, so we're not, this is going to go to 0, so we aren't interested in that. Then we have a meters here, so a plus c, and then a meters here, which will be a plus 1 for that mass transfer coefficient. And we want to set that equal to 0 because we want it to be dimensionless, so none of the units will appear. So now let's look at the seconds. So looking at this first group, there's seconds in the denominator. So that'll be a negative a. And then we don't see seconds again until that mass transfer coefficient, and that will just be in the denominator as well. So a negative 1, set that equal to 0. And we get that a is going to equal negative 1. So then if we plug this in, we will see that, sorry, negative 1. So that will be negative 2 plus c plus 1 will equal 0. So that just leaves you with negative 1 plus c equals 0. So we get that c equals 1. So if we write out this again, we will see that the pi group for 1 will be that diffusion coefficient to the negative 1 power. Oh, I can rewrite this actually. So we'll see that that diffusion coefficient is going to be in the denominator. And that that diameter is going to be in the numerator at just a power of 1. And then this coefficient, the mass transfer coefficient, is just going to be to a power of 1. And that's our first pi group. Now, looking at this second pi group, we see that these variables are the same. And then when we compare the mass transfer coefficient to the velocity in terms of units, they're also the same. So we don't have to do this again because we know how the units play out for the coefficients of the variables. So we can just put that for the second pi group, instead of the mass transfer coefficient, we're going to put velocity and that diameter all over that diffusion coefficient. Also, one thing I think I forgot to mention is that the liquid is volatile, and that's really key for this problem. And also, I wanted to talk about that this is just a characteristic length, the diameter. So let's say it's an equilateral shaped pipe. Then maybe we would put the side as the characteristic length in that case. Okay, so now let's just look at the third and final pi group. So let's look at those units again. So same thing as before, just for those core groups, would be that the meters squared per second kilograms per meters cubed for that density, and then meters for that characteristic length. But the variable we're interested in for the non-core would be that viscosity, which would be that kilograms per meters per second. So let's look at this. So kilograms is in two terms now. So this one is going to stay the same, and it's just going to be to a first power for this whole variable. So that means that we need to change it over on this side and make it a -1 so that that kilogram moves to the bottom. So we're going to say that H is -1. Let's look at meters. So we have 2g because that's meters squared in the numerator. So since this is going to be a negative power, that's going to be flipped. So that's actually going to be a plus 3h. Actually, I don't need the h, because we already know that that coefficient is going to be -1. Then we want to do a plus I for that meters, and then a -1 for that meters in the denominator for that viscosity variable. Now let's look at the seconds. So negative g for that first diffusion coefficient. And then we don't see seconds again until the last variable for viscosity, and that seconds is going to be in the denominator as well. So we're just going to do a -1 and set that equal to 0. Oops, set that equal to 0 as well, because once again, dimensionless, we don't want these units to appear. So then G is just going to equal -1. Okay, I want to rewrite that. And now we want to look at the meters, so we can plug in for what we have. So -1 for the g, which will be -2 plus 3 plus I minus 1 to equal that 0. So then those are just going to cancel out so that I is going to equal 0. So let's put that in for the pi 3. This third pi group is going to end up having, so let's see, so g -1, so the diffusion coefficient is going to be on the bottom again. H is going to be a -1, so we want that density to be on the bottom as well. I is 0, and then the viscosity is to the power of 1, so that viscosity will be on the top. So now let's look at the units again for each of these pi groups and try and relate it back to some known dimensionless groups. So looking at this pi 1, we can see just by definition, we know that it resembles or is the Sherwood number. And then looking at that second dimensionless group, oops, that's the second one. Second one's going to be the Peclet number, the PE. This one's the Sherwood number, just by definition. And then for the third one, let's move down. For the third one, it's going to be the Schmidt number. So if I just do the pi 2 over pi 3, since we're interested in Reynolds and not really the Peclet, what I could do is divide that. So put those variables in there. Oops. And if we reduce this, then we can get it to that diameter, velocity, and density on the numerator, and that viscosity on the bottom, which is the Reynolds number in terms of those variables. So that's how we can get these dimensionless groups, and later we will use these dimensionless groups to relate to one another in an equation.